Today's tale is the tale of the architect. The context, for those who missed the beginning of yesterday, is a series of stories. The same thing. You're going to see some of the same images keep repeating, but the story about them changes slightly and gradually develops. That's the intention. And I show less and less of the same images and more new things, but I hope the comments develop. And of course, we're basing this on Pasolini. The two storytellers are Sam Hardingham and myself, and as you probably all know by now, Sam's got a broken wrist and isn't here, which is very sad. But that's the basis that we try and share these stories. And what we're looking for is a kind of new theory, or perhaps better still to describe it as a new discipline. And in particular, I was arguing yesterday that it implies new roles for all the key players. They're going to change the roles of the citizen, the architect, the building, computer, and the environment. I emphasize that, of course, you may not agree with me about how I think they're going to change, but I think it's fair that I can ask you in return how you think things will develop if I'm wrong, what alternatives are there. And in fact, I can see some alternatives, and I know there are alternative views, so that's not a kind of mischievous question. I'm really trying to say, I don't think we can accept the status quo any longer, and I'll try and expand on that. Yesterday we had the storyteller story, and to summarize that in just 3 or 4 slides, we talked a lot about the global vision from Butlers and Fuller, Nine Chains to the Moon in the 30s, setting the context for a concern about needing to take a global approach to all our energy and resource problems, and his observation that the Earth didn't have an operating manual, so he wrote one. And the emergence at the critical period, I spent quite a few minutes yesterday recapping yesterday on the context of the 60s and 70s and where all this started, and in particular Buckminster Fuller's attempt to involve the world's architectural and design students on the grounds that they were the ones being trained from a generalist point of view and had the comprehensive vision that was necessary to address some of these issues. And the key moments round about 1965 when all this gelled, and the idea that you would, if you looked at the contemporary press of the architectural design and so on of that period, think it had already happened. And then it got to the 70s and there was nothing. Mid-70s, oil crisis in Britain, Thatcher got into power, everything went into a dreadful downwards spiral. And so we've got the bizarre situation now that many of those same issues are being revisited. However, very many significant things have changed in the meantime. It's not like going back, it's just that the issues which were kind of like pretending they'd emerged then really could be emerging now, but in a different context and with different technologies, which puts a slightly different spin on it. So the story has to be retold. And we talked a bit about the misfits, the two stories of architecture going on together. The one being told by those people who attended this conference, people like Archigram Group, like Cedric Price and so on, one kind of group. And the other kind of mainstream architecture being represented still, and some schools of architecture at that point had only just changed over to accepting that Bartlett in particular had only changed relatively recently at that point from rendering classical content. And I suggested that I saw the problem not as so much a box of bricks approach then, but as a packet of seeds, the notion, and I'll explain a little bit more today and tomorrow and the rest of the week what I mean. What would a packet of seeds approach mean as opposed to a box of bricks? And we talk tomorrow about building construction. I'll particularly explain why people thought in the 60s and 70s that a kind of kit of parts approach might be useful and what went wrong with it and what can now replace it. And the other thing I did yesterday was introduce the notion of autotectonics. This is a made-up word, but it's quite nice because in my terminology it gives us a name for this new discipline, so those words get put together and imply some kind of other strategy. And each day I'm going to expand a little bit more on what I mean until I put the whole story together on the last day. Oh, sorry, this is the key, perhaps the key role slide yesterday, was my implications about, or my understanding of the way those key roles will change. And this is the bit which is also open to question from you. However, my vision is that the architect has to move upstream, as it were, and talk in more generic terms, which I claim comes naturally to most architects anyway. They just don't express it generically. And this would imply, actually, instead of expressing individual one-off buildings as drawings and so on, it would imply establishing the fundamental rules that would generate alternative variations on their seeds. This establishes a situation where the user can move up into the vacuum and play a much more active role. But I believe that the environment too has to be an active participant. It's no good talking about this as if it's some kind of neutral thing outside. Because architecture has such a mammoth impact now on the environment, it's changing the climate, buildings are part of that total ecosystem. There's no way out of that loop. They're not, if something's very small and makes a very small impact, then you can ignore it and the ecosystem will take care of it. The problem is now that the impact of waste energy, carbon in the atmosphere, and waste heat and problems with resources has got to the point where it's probable or possible that the environment can no longer respond fast enough, and I'll come back to that point on Friday. The means of construction are changing, and I need to deal with that tomorrow because that's both a positive thing and a problem. All these things have two sides to them. Obviously, I'm talking mainly as an optimist. That is, I can see through this at least one route, and possibly others, which lead to a future where all the things that we might, or I might like to see happen, like the user being more active, the environment being responded to in a better way, can happen. However, each of these comes with a downside. And finally, the computer, which is the most extreme of these, I believe its role is as an evolutionary accelerator. I'm not interested in it doing drawings and modeling, but you're going to see at the end of this lecture both the positive and downside of that. I'm going to, against having promised not to show any kind of ordinary computer models, I am going to show just a few at the end of today, to explain a problem and also a potential, a real potential, depending on how architects play it, hence the importance of the architect's role. Although I mentioned Fuller quite a lot yesterday, I didn't show this particular example. This is absolutely typical of the kind of way the press treat this issue. This book has a very serious intent. It was written at a time when there was a great deal of negativity about the environment going on, and the book was written by the publisher's intention was to create a more positive view. So far, so good. And to do that, they imported some quite good writers whose work is widely quoted throughout the book, or it's been ghosted for them as if they wrote it. That's all fine. Now the problem comes, and watch this very carefully, when you look on the back cover. There's the back cover, and let me show you a close-up of that top quote. It says, already on board a spaceship, so far so good, that's Fuller's argument about the spaceship Earth, and there are an infinite number of resources. Well, he says that unfortunately, well, you'll see in a minute, that will never run out, and there's an infinite amount of space in which you can get rid of all your filth. And this is attributed as a quotation to Buttons to Fuller. Now this is highly irresponsible. When you go inside, and notice I've scribbled on page 79, look what 79 actually says, picking up that, and all your filth and waste, those resources. But, it is a closed system. You can't do that. And that's the kind of system here. We have anything but an infinite number of resources. We have just enough to make the experiment and so on. It's the exact reverse point of the back cover. Now this is a really serious problem that we've been having with all the commentary on everybody's attempts, whether it's by architecture historians or the press, or anybody else, to make impact in this field. When you get a responsible publisher, this is Collier Books no less, producing a cover story of such gross and deliberate absolute misrepresentation of someone's views. I can't imagine what Fuller thought if he ever saw this quotation, apparently a quotation attributed to him. Now, where does the architect come into all this? That's the background. The first problem with architecture is that most disciplines have a theory, and that theory is clearly set out in key textbooks, treatises, and so on. And architecture doesn't have one. Now, of course, you could argue that's an advantage, and perhaps in a way we are arguing that because it means we're not hidebound to one particular way. But I'm saying by implication we are hidebound, and we're hidebound to one which comes out of this line from books like Vitruvius. Now, just out of interest, can I just do a straw poll? How many of the people in the room actually read Vitruvius? One. There's nothing to be there's nothing to worry about, because in a way, I mean, I won't, this is unfair to ask you what your reaction. It's quite interesting what it deals with and how it deals with it. But one of the first things is, although it's cited as being a theory of architecture, I don't think you could call it a theory in the same way. Let's discuss theories for a second. There are two kinds of theories. There are theories that explain how something happens, like Newton explains particular relationships between a force and movement and so on, and that's a theory of explanation. And most science comes into that category. That is, the thing, the phenomena, precedes the theory. The theory then explains it. That's a bit of a problem with architecture because, in most cases, you're not trying to explain something that has happened. You want the theory to do something in the future, therefore can it interpolate further? Well, of course, you can apply, say, Newtonian equations or later theories from relativity to predicting, say, the movement of a train or the behavior of a space shuttle. However, it isn't actually creating the object, it's just predicting its behavior. So those kind of theories are like testing theories that enable us to evaluate something that hasn't been built, like from a virtual prototype. But they don't tell us how to actually get the virtual prototype onto paper. So what you actually need is another kind of theory, which is a theory for doing things. Now, theories of that sort are relatively rare. They come up in cookbooks, quite a good example, or knitting instructions. They're kind of like a recipe. But a recipe is a very low order kind of set of instructions. And so you also get pattern books in architecture, I'll touch on in a minute, which are sort of laying down a way of doing which you basically copy. Well, that isn't really a theory either. It's a recipe. I think that's a better word for it. So what would we expect to find in a theory book, and what are in these books? And this is very unfair on Alberti. It's just that there are, as a vogue at the moment for writing about Alberti, as if, again, this represented theory. But when you look inside, this is very mean, because these two illustrations are from a particular edition, but I checked two editions, and they each contain an image of this kind. There is some object, usually a large sculpture of usually a naked female, being hung by a rope. Now, the question is what? Actually, this one's rather good. It's got the rope around her waist instead of her neck. It's a small improvement. But what is this illustrating? It occupies a whole, somebody took some time to make this engraving. Well, actually, what it's illustrating is a weight being held by one rope. That's the whole point. The next image is a weight being held by two ropes. So it starts to explain pulley systems. So what we actually find is an enormous amount of explanation of very simple physical phenomena, and vast illustrations describing this very elaborately. But actually, all they come down to be are basically the theories of, explanations of. This isn't telling what, you're simply explaining how the pulley system works. So we're back with Newtonian physics. So in a sense, when you start to look at the book more carefully, it doesn't provide the kind of theory that would actually help us design. And again, so it divides the book. And anyway, I'm interested to know if anyone thinks this is an unfair comment. The book divides, in my mind, into things which are theories of, that is, like the same equivalent of equations of motion. Or they're recipe books, pattern book type things. Palladio is much more straightforward. It's a recipe book, it's a pattern book. He shows his designs, you copy them. The whole of Europe is covered with fake Palladian buildings, or neo-Palladian. Durand. What does Durand lessons? Well, again, it's a knitting pattern. It's describing architecture as some kind of methodology. Now, the methodological kind of side of things came to a head in the 60s with the beginnings of people like Christopher Alexander, writing things about design methods, which were going to be some kind of attempt to be an explanation for, rather than explanation of. And a great deal of London was built, for better or worse, from these pattern books. It was very, it provided, on the good side, what did it provide on the good side? On the good side, it provided well-tested, well-tried economic designs, which produced a good visual conformity, which produced a lot of the squares and patterns of houses in London, which we know, and so far so good. But there were two big problems. One was that as they got smaller and smaller and smaller, the kind of the implication was that the style of life that was in this was only kind of like a copy of the style of life of the big houses, and the plans didn't really ever work again at the small scale. So that was problem one. But the point was that the builder could sell very small copies of what looked like a kind of gentrified style of living, and that was a marketable commodity. So that I see as problem one. Problem two is it's raised its ugly head again, the ugly side of it, with the notion at the moment of building codes, where we're being persuaded that experts, particularly those coming from Prince Charles's school, can somehow codify good present practice, like good and bad manners, and somehow everyone, if they conform to this, will be able to produce better buildings. And now Prescott is backing that idea rather than Richard Rogers' report. So watch that one with concern, because again, we could have this kind of thing being imposed. That is a pattern book approach. But it's not all bad news. Most of what I'm saying, it depends how it gets interpreted and exactly who's in control. You could imagine the pattern books all being written by Palladio or Richard Rogers or whatever, and we might then get a better environment in general, because we're talking about architects of smaller buildings not designing a significant number. I've been trying to get the statistic of buildings over £250,000 in the UK. Architects design about 40% of them. But of smaller buildings, we think it's probably more like 10%. But nobody seems to be able to give me a figure on this. Does anyone know? Anyone got a better figure? And therefore the argument coming from the government is that if you codify the building design, then we will get in general a better environment. And it's one of those arguments which could be true, but probably won't be. Then, of course, there's the traditional role of the architect as master builder. Architects have lost their image and position in the building team, and this is an absolutely crucial thing to the architect's story, because they haven't managed to invent a new role. In the Middle Ages, every cathedral, of course, there were always sculptural representations of the architect. These were very important people in society. They dined at high level, as it were, but they had a hands-on approach to the building, which enabled them to actually lay out the stones themselves on site. They're always represented with the tools of their trade, which they were able to do not just to do the designs, but to actually do the stone, the stereography on site, to cut the complex stones for the vaults. So that was the master builder approach to architecture, and that put up most of our heritage of Gothic cathedrals. And even their tombs, which occur in significant places like Westminster Abbey, again still captured with the iconographic representation of the building and the tools their staff are measuring, their set square for setting out the thing, and so on. Now, some architects and some professions have tried to hang on to that role, but there starts to be a tension. This cartoon I pinched from Adrian Forty's book without his permission. But in a way, it epitomizes this kind of, or captures very nicely, this notion of, two of the notions we're talking about. One is the role in which the architect sees himself, and the other is the problem of the user and the client, which is what we were discussing yesterday, and this tension. So in this particular cartoon, there is clearly no intention of resolving this issue at all. We've got a clear indication of what's going to happen. This, though, is an advert from Architecture Journal, and I'm sorry that's such a bad slide, but this the servants of the architect are around him. The chair, the comfortable chair, it says reserved for the local authority architect. So this is an advert, and this is not meant to be a joke. This is an advertisement for something, and it's a clear implication of one reading of what the architect's role is. Now, why do we need architects at all? Well, when you get to things that are very big, like a city, this is Suzhou in China, described by Marco Polo as one of the two most beautiful cities in the world. You start to have drawings. Somebody has to put a plan to it. This requires a planner or an architect because there are too many people involved, and it characteristically has the moat and a particular kind of layout and so on, based as it happens on the layout of the Forbidden Palace, of which it is which becomes a kind of model for ideal planning. So I'm just really making a loose point here that things that were very big require drawings. The other thing that was very big that required drawings were boats. And again, there was this relationship between the making, the drawing, the forming. Is a crucial element, and when that's the kind of element where drawings are working well. The problem is when this starts to break down. So this plan epitomizes the two problems, the problem of the planning and the problem of the big objects, both of which mean there is a possible loss of directness between the forming and the making. Possible loss. And it's the possible loss and the actual loss that's occurred in the last 100 years, which is the cause for concern this morning. But let me show you the counter trend, because the counter trend is that there is a chance of regaining control. I'm going to take this from yachts. This is where the yacht designer Ron Holland lives and works, or did, he's moved actually. And in that cottage is a great deal of computing equipment. These photographs are now more than 10 years old, but what goes on is much the same. Ron is not in fact designing at the computer. The way he designs is like this, is that he works at a traditional flat drawing table, and he sets out the lines of the boat using the traditional method of bending, splining. It used to be wood, because wood was a direct metaphor in terms of visual terms and physical terms, but also it was an analogue to the actual behavior of bending a plank. You bend a thin strip of wood. Now, interestingly, the kind of curves you get from this, still very good, even if you make them in aluminium or steel, to the kind of curves which water is going to flow smoothly over them. You don't get sort of kinks and bumps if you try and bend something that way, which you can get on the computer screen. But they are backed up in the rest of the college by a team of engineers and designers who are using sophisticated computer techniques to do all the other side of the work. That is, for example, to do the hydrostatic calculations, to make sure that the curves which are true in this plane meet truly in this plane, because as you saw from that, it's very interesting that the galleon I showed a few minutes ago, the 74-gun man of war, is rolled over in the picture. You can actually see better that the lines work fully in 3D, which has always been a problem, to ensure you can easily understand that that's a smooth curve in one plane and that's a smooth curve in the other plane. But it's quite difficult to visualize sufficiently accurately that you've got a smooth transition of a curve in 3 dimensions, and that's, of course, what you're going to make, although it may be made by making frames this way and then making planks this way. So there is a clear relationship between the way it's being drawn and the way it's going to be made in terms of the planks. And of course, that holds true of some construction techniques still. So actually what you've got here is the best of both worlds. Ron Holland here is using his skill and judgment, all his experience of yacht design, to evaluate and actually put in the lines. And the computer is using all its computational power to make sure that these are smooth in 3D. But he still keeps checking backwards and forwards, because it's very easy to explain to a computer what a fair, the word is fair curve is. But what about a smooth bump on a fair curve? How do you explain that? I'm just going to digress in a moment. Well, I'll digress at this point about Frank Gehry, because Chris Jakarta, who works in was telling the story very nicely the other day. Frank has the same problem. Frank gets hold of a yeah. Actually, that won't do. I need a piece. Anyone got a piece of paper? Okay. Frank Gehry designs by taking cardboard and thin paper and bending shapes. You can uncurve it again so that it comes out of a flat sheet, so it's much easier to manufacture. But complex curves like the Bahama ship get their rigidity from the fact that in fact they can't be developed. That's a non-developable shape. You can't flatten that out. However, Frank also has a habit so that the computer can very easily interpret the model. And we'll see this in a minute. But then Frank has a nasty habit of putting kinks into the thing. And then what happens? He likes these kinks, you see. And then the computer, of course, gets hold of this and it smooths this kink out. So it comes back all nice and smooth and rounded again. And then Frank sees it and says, "Where's my fucking kink gone? What's on that bloody computer?" You see? Now this is a real problem of interpretation. How is the computer to understand that what's intentional and can be smoothed out, and what is intentionally a kink and must be left? How do you explain that difference? How is it to understand? So there's an enormous problem here, credibility problem, between different kinds of working method and different kinds of comprehension of what's going on. But Ron is resolving it by an iterative process between his eye and his judgment and the computer model. The instructions to cut this this aluminium rib has been cut with a laser cutter. And of course that's back to the same idea of making wooden frames for the boat. That has, these instructions to cut this laser have come straight from the computer. The yard's some 7,000 miles away or whatever, 3,000 miles away. But the tolerances, the very, very fine tolerances of this are being directly controlled by the yacht designer. So he has regained control of the manufacturing process, the making process. It's back to being in control of the potter's wheel or the lathe again. And so when you start to fit these together to make hulls, it's not fanciful to say that Ron, in fact that's Ron there, Ron is in fact constructing this boat even when he's not there, he's 3,000 miles away. So again, what was a risk that the architect would lose control of the process is something that could be regained through the technology. However, it could also equally well get lost even worse through this process. So the next question is, why then is Ron Holland based in Ireland? Why isn't he based right next to the factory? Well, the answer is to do with the water in the distance. You have to test the hulls. And the advantage of Ireland is that the weather conditions are very changeable. On the south coast of Ireland, the wind and wave patterns change very rapidly during a day. So it means very quickly you can put a boat through a very considerable range of different racing conditions. Whereas if you live off, say, New Island in New York, it stays the same wind, same direction, same strength, same wind pattern, same wave pattern for days on end, weeks on end. So you have to test things back in the real world. So however much we become dependent on computer modeling to simulate the behavior of things, in the end, it has to be tested, and that's why he's located where the water is for the testing. And I'm going to argue that exactly that same process of moving from the computer model to the actual made form is how Frank Gehry and others are operating. Now I want to say a little bit more about my seeds. I'm going to keep coming back to the seeds issue. This little structural system, it's just two structural units. It was meant to fit together and make lots of different complicated shapes. What I didn't say yesterday, I did tell you I got involved in using computers, but a couple of bits of the story I didn't tell. It was extremely difficult to design with and visualize these shapes, and even more difficult to draw them, which is why the idea was that without cutting any unit, these things would creep their way around other existing parts of the building and so on. So I'd solved half the problem. The problem was I was still putting the data in, and I was putting the data in by means of this drawing board which works with hexagonal coordinates. Skip that bit of the story, but it's to do with getting them in as integers, because we couldn't store real numbers in the computers, we didn't have enough storage space. And anyway, real numbers aren't accurate enough. But integers, these are whole numbers in 3D space, allow you to describe these complex structures in whole numbers. So everything fits together absolutely perfectly. The problem is you need a special drawing board, you have to think in a special way, and this is altogether extremely tedious too. So that led me to my first experiment with a seed. In this case, it's called a seed because it contains every possible orientation of the two. These are the two basic units, and each possible way when they can be in space. So in fact, there are 20, I can't even remember now, 12 ways round this one can be in space, and 6 ways round this one can be, making 18 possible ways in all. So they're put together in one object. The reason for that being so it stays closed. That as we now go through the manipulations, there aren't going to be holes developing in the structure. So you expand it. The idea was intrinsically two different things. One, I wanted to try to develop this biological analogy which I'd shown yesterday with DNA, the idea of coding and some kind of seed. And the other was intrinsic laziness, that I never ever wanted to have to go to the trouble of putting all that data in ever again in my life. And so I was going to grow it, which is altogether a nice, lazy solution. And that, I showed yesterday too, the circular cathode ray tube, there is the seed on it. Now I've got to explain now what happens there today. And you could deal with those are how you represent each of those orientations in space. That's just one unit being moved around different ways. Okay? And you can, of course, combine these. In those days, computing wasn't sufficiently interactive. You couldn't actually pick one of these up with a mouse or a light pen and move it to somewhere else. But the idea was that theoretically, you probably could soon-ish, perhaps, if you did enough computer programming. However, we didn't do it that way. We worked from that seed. That's that little seed represented on the screen. And here it's growing it into a bigger structure automatically. So all the data for these other units has never been entered. It's made that data itself. Now, this is absolutely crucial change in strategy. In fact, there were two seeds, that one and that one, which grew it were like two different kind of variants on the structure. And here you go. There's the seed at the top. And the first instruction is grow. So it simply just makes more and more units. It goes on growing this until you get to the size of structure you want. As I explained yesterday, you can't hold too many of the units on the screen simultaneously. So these are simplified drawings, but you can see enough of what's going on. These instruction is shear. You get hold of the structure, you shear it along a shear line, but it fills in. These are units like, as it were, on their edges in between, so it stays as a completely coherent structure, structurally and waterproof. And here we're bending it and making the structure flow to a different shape. So this drawing, after which of course is off the screen, but at the beginning here is the building brief. And normally you go from the building brief into building some kind of data structure as a one-off process. The intention here was to seed the data structure with a minimum amount of data, but that somehow encaptured the generic concept of the building. And then you'd run this cultivation program that grew it, stretched it, decided to cut it, trim it, until you got the overall thing to the shape you wanted. So this is a more complex set of maneuvers. Here I'm pulling it up now. Here we're stretching it. Now the limitations to this, as I said, this was successful in as much as it produced the kind of configurations we wanted, and they've all come just from that seed. So there was no question of having to enter all that data ever again. And that's how it was actually coded in 3D space in integers. And all that word was packed into just one word of the computer language, which was basically my first attempt at DNA. So far part of the analogy works, but only part. The problem with it is it's only got 2 units, it only makes a very, very limited range of kinds of thing, although the shapes obviously are very varied between these. They nevertheless all obviously constrain themselves to this particular kind of geometry. And so the question I was obviously teasing myself with was to what extent this could be generalized. Could we write some generalized DNA code that could be applied to other kinds of structure, more flexible, less formal, and so forth? And what I don't think many people in the room know, but I've shown these slides often before, many people are familiar with them. You may not have seen this, which is how this thing actually fits in sight. These are some existing buildings. There's another at the back there, which is not on this drawing, because we were building these at the same time. And they were all actually constructed. So this thing actually is a building. It was structurally tested in the Cambridge engineering labs, strain gauges, aluminium prototypes, finite element analysis of that structural system, so it tells you which units are overstressed and so on, automatically. That's all then became part of the feedback, and indeed we constructed it. But it went up in the fog, which was quite amusing. It was all prefabricated. Because what I was doing was experimenting with trying to treat the whole building like a set of, it was still component box of bricks oriented, so the whole thing arrived like a kit of parts and was just put together. But I was still back of my mind on the generalization kick. And it wasn't until about, 1990 that we managed to get the kind of computing power and a group of students that could explore this. And here are some of the very first examples. This is a student called Ichiro, and Ichiro in 1991 was one of the first students to successfully use a 3D cellular automata to grow and evolve and develop forms. I'm going to explain on Thursday how the actual cellular automata technique works. For the moment, we're just looking at the idea of generating these forms using generative techniques. So this particular one starts to include another thing called a genetic algorithm, which again I'll explain more fully, but it's a way of controlling this growth in a direct analogy with genetics in biology. And these are some of the first experiments that managed to run and generate varying forms which describe the data structure in response to changing environmental conditions. So these models, there's some kind of putative building in the middle. These models are things like the solar movement and so on, environmental conditions, which are controlling the kind of modeling of the data structure as it evolves and develops. Now I have to repeat again a point that I'll keep hammering away at. These do not represent proposals for the shape of the finished building. That's the confusion about the blobby texture. These were not intended to be the form of the building. These were descriptions of the envelopes of the data structure. It's a very different thing. And I'll show in a minute how that's interpreted. So that was Ichiro, and he was followed by a group, lots of other students. This is, I've shown this many times before, but this is Manet and Thomas in a couple of years later. And the starts with the same little cube in the middle you can see in that. I'm going to explain on Thursday how the rules for this work, but what you have to understand for the moment is simply that there are rules, there's genetic code associated with each of these cubes. And that code causes the cells to split in a pretty well direct analogy with what happens when you start off as a single cell being. The single cell splits and divides until you get to the complexity of a human being or an oak tree. And what's happening here on the screen is exactly the same. There are rules, transition rules they're called, and that I'm going to explain. But for the minute, just those rules, they're like DNA, and they're like the rules that are in the DNA for generating cellular growth. And at the moment, they're all identical. You start off as all identical cells. However, and you'll see in a second, when this reaches a kind of stasis point, some of the cells start to specialize. As you presumably know, that in your body there are many specialist cells. The ones at the back of the eye are the ones I particularly like as an example, where at the end of the rods there is just one molecule which is sensitive to a particular frequency of light. When a particular frequency of light falls on it, it changes that molecule to change its geometry, and that causes a chemical to flow. That causes an electrical signal. The electrical signal goes to the brain. The brain gets millions of these from both eyes crossed over upside down, and causes, and from all that it makes the 3D representation of the brain of what you see is out there. Now, what you see out there, what you're seeing, we always have this question, are we sharing it or not? Is it the same for us all or not? But it's all made only from those electrical impulses from those single cells. So they're specialist cells, but they started off identical to all other cells in the body. And in some animals, the cells can change. Insects and animals that are able to repair broken legs and arms and grow new ones, can actually change the cells. Cells that were specialized in one thing can regeneralize and then form the growth again. It's a most extraordinary business. And here you see the cells are specialized now. They've changed shape, they've changed color, they've changed geometry. So let me reiterate another point about the difference between development and evolution. This is one development. It started from one single seed and gone through a development process to some resultant form. Now, the first question I have to ask myself is, do I use the word emergent or not? Because that's a very overused and misused word. We're back into the Lilliput syndrome problem again. However, there is a sense in which it's emergent. That is, although the rules, the transition rules, are strictly deterministic, the actual output is often surprising. So, if the complexity of the result is more than the complexity predicated by the simplicity of the rules, then in one sense it's quite correct to call that emergent. But I have to make a differentiation between myself and various other people talking about emergence, who seem to think that emergence can come from nothing. Somehow out of all this computer goo will come something. I don't think that's true. I think we still need to sow intentionality. So I'm picking a route which you might even see as relatively conservative, which is to say the seed up here has instructions in it which are intentionality, which I see as the equivalent of instructions in DNA. I see those as it were, meaningful intention of producing a form. Our DNA does not intend to go and produce something else when it's going through one growth sequence. However, from generation to generation, it can evolve, and that's the next point. Each time, this is just one run of the software. Each time it runs, it produces something different because it's also able to evolve. And absolutely clear, I'm describing that as development. The biological terms are things like epigenetic development or ontogeny. I'm saying that we're using the simple term development. That's one development, one cycle of growth, one tree. However, these are the same software at another stage in its evolutionary cycle. Through millions of iterations, it's developed and changed the forms that are resulting. It's the same essential set of initial rules, but the mapping conditions, for example, to the external form have changed. I think it's fair to say that it's closely analogous to what's happened in terms of DNA learning to map to different forms. I mentioned on the first day that 30% of your DNA is the same as spinach. So those same instructions that cause the spinach to grow and make spinach are causing you to grow and make you, but they're clearly going to look like spinach. So something has changed, and it's roughly equivalent, and I will expand a little bit more clearly on that. So that's not a very good scientific explanation, but I hope it will do for the minute. I always share this example because just in case anyone wants to try and do any of these things, I have to say that it's very difficult. And for every successful one of these pieces of software, we had an awful lot of failures. This one was a catastrophic failure. It's very complicated, first of all. There are two 2D cellular automata, which I'm going to explain. I'll leave that explanation until Thursday. They drive a three-dimensional cellular automata, but basically it's a heap of these cells, which are two kinds, representing the structure and the environment. And they're trying to make, between them, a surface, which is this yellow thing, which is meant to be an optimal solar surface, in terms of both its shading of too much solar energy and surfaces for collecting the maximum solar energy. However, without me making any further explanation, I hope it's obvious that that's never going to be optimal anything. And this program ran. Maybe I can show you a run. And here you see the cellular growth occurring. And here you see it trying to build the surfaces. Now, it just got itself in a twist, well and truly. And every run just got itself in a twist. So that was a complete and absolute failure. And I just put this in as an ominous warning, because if you want to try and do this, you have to accept a very large number of unsuccessful attempts. We don't even know why that happened. It just finally got abandoned. So that's just a little kind of warning. And nature, of course, has a very, very large number of unsuccessful experiments. Profligate prototyping.